quite an interesting topic today. We're going to be talking about systematics handling in high-energy physics. And we have two different contributions here today. One contribution that we're going to start with is by Ben Messerly, who's a postdoc at the University of Minnesota and part of the MINERVA collaboration. There was a paper he was recently brought out where he was a part of, describing the MINERVA analysis toolkit. And now in this first contribution, he's going to talk to us a bit about this. And then we have a second contribution that we'll get to after this. Ben?
Thanks, Alex. Thank you for having me. I've had a good time learning about the IRIS group, and I'm curious what sort of collaboration we might be able to have, and I hope you enjoy hearing about our toolkit. We're a rather small operation, I think, compared to the IRIS group, which has a very nice looking website. No website for us. This is just Google Slides, default templates. Okay, so I did most of this work at the University of Pittsburgh. And yeah, as Alex said, now I'm at the University of Minnesota. And this is all, of course, for the MINERVA experiment. Calling in from beautiful spring weather in Minnesota, where the cherry blossoms are blooming and everything is gorgeous here. So I'm going to talk about, I'll introduce the mat. In items 2 and 3, there are a couple, I think what I see as the critical offerings that the mat has. Examples in 4, and if I have time, I'll talk about item number 5, otherwise I'll just skim over it. But it's about the importance of how experiments design their data and provide access to the users. So as you've probably gathered, the MINERVA analysis toolkit is a HEP physics analysis software toolkit, and taken wholesale, it can provide you with an entire event selection and data manipulation system. When we were designing this, we placed strong emphasis on transparent treatment of systematics. Systematics play a central role in the analysis flow, and we implement the many universe error method. You may not know it by this name, but I think this is the basic idea of that a lot of HEP experiments use to calculate systematics. And another important aspect of the MAT is that it provides the opportunity to centralize and standardize systematics across an experiment. It's written in root and C++ base with a translation into Python. It's with strong emphasis on systematics, we sort of didn't emphasize as much the other things. So it uses event loops. We provide bare bones and minimal objects that we intended for other users to build up more sophisticated tools or slick interfaces out of. To provide you some context, this is built on the MINERVA experiment, which measures neutrino cross-sections at Fermilab in the NUMMI beamline. We've been about 50 to 100 collaborators steady state for the last more than a decade now. We have 30 plus cross-section publications and still going strong with all the data, which is really great. And it's providing sort of bridging the gap to when Dune turns on and starts taking data, it needs to have very well measured neutrino cross-sections to hammer down systematics for Dune's physics program. We collected 30 E20 or so POT between 2009 and 2019, and now we're entering the data preservation era. So no beam, but still tons of data to analyze and very active analysis program. When I joined the experiment, MINERVA's analysis software used the sort of make class, Root's make class event looping paradigm, if you're familiar with that. And while it had an excellent histogram object, which I'll talk about next, it sort of had an ad hoc systematics system that poor graduate students would spend so much time validating the feasibility of their analysis that when it came time to look at systematics, they had a rather poor system to work with, and they were really sort of fixing and hacking on the fly. So the MAT has tried to overhaul the systematics, although it keeps the event looping idea. And it is now what is used by all MINERvA analyzers, and it's the basis of the data preservation program, which will be eventually releasing more publicly with our data set and a lot of templates and tools to run your own analysis on our data. But yeah, the focus from going from pre-MAT to MAT was to provide a smooth transition for analyzers, because we were sort of rebuilding the ship while we were sailing it, and we needed it to current users to pick up the new system rather smoothly. So we kept a lot of the things the same and just tried to overhaul the systematics. The goals of the MAT, if this statement looks familiar, you'll see in a second. Okay, extend the reach of the intensity frontier Fermilab experiments by creating greater functionality, reducing time to insight, lowering the barriers for small teams, streamlining analysis preservation, reproducibility, and reuse. That is actually your analysis systems group goals, and I could not have put it better myself for what Matt's goals are. So Matt has a lot of overlap with these goals, and we say as much in the VCHEP paper that is linked in the Indico, and I'll link later on. So just to anchor you and give you something concrete to think about for what sort of things we calculate so regularly with this analysis toolkit, we're calculating neutrino interaction cross-sections. And really what we're doing is a differential cross-section where we have the signal selection in the background, going through some migration or unfolding here, and then normalized by the efficiency, the integrated flux, neutrino flux, the number of interaction targets, and then the bin width. So when we say many universe error method, what we mean is that the cross-section is calculated in many Monte Carlo universes corresponding to systematic uncertainties. So every time there's a Monte Carlo input here, for example, the background, we'll calculate the background many, many, many times, where in each case we've tweaked some parameter and gotten a slightly different result. And then that is how we calculate systematics. I think this is quite a common way of doing things in HEP, but there aren't actually many citations, and there's not a lot of language that I've been able to find to put us all in the same place. So we're calling
just a comment real quick. I think this is the more or less standard frequentist approach to dealing with systematic errors that we use in CMS. I'm not sure. I'm sure Atlas is something similar too, but you basically tweak a systematic within its you take a systematic error in the central value, you tweak that according to some random pull from its expected error, and then you recalculate the cross-section based on this in order to form a confidence interval.
Exactly.
Okay, yeah, this is what we use too. We don't call it many universes. It doesn't really have a name. It mostly just refers to like Bob Cousins' slides from years ago.
Yeah. So, okay, well, if you want to adopt the language, that's what we're calling it. It's not maybe a great name because of its weird overlap with quantum foundations ideas of, many universes or multi-universes. But there's another raised hand from Nick. Do you want to interject now?
Yeah. Can you clarify when you say like in many? Does this mean, each uncertainty, you can think of it as like some dimension, some nuisance parameter in your parameter vector, in your, space of parameters, right?
That's right.
So when you say universe, does that mean you've shifted along a specific, along the axis, essentially, along each dimension? Or do you mean you sample randomly in the whole space and compute ensemble statistics from those samples?
If I'm understanding your question correctly, I think I'm talking about the first one. So to be specific, if you have some uncertainty on a calibration parameter, you may tweak that in the simulation, and that calibration parameter will then propagate all the way down the line to various reconstructed quantities and so on. And maybe you may tweak more than one source of systematic at once in a single universe. But the simplest way to think about it is you have some uncertainty on a calibration parameter, you tweak it, and you propagate that tweak, that parameter tweak, all the way through the simulation, and you reperform this entire cross-section calculation with just that single tweak.
Okay, that is qualitatively different from what we do then. Okay.
Well, no, it is the same. We go along the axis. That's what he's saying.
But we typically go along we randomly sample from all the axes every single time we make I thought we did.
Okay, so
sorry to cut this short. It might be important that we like agree on the understanding here, but we shouldn't spend too much time discussing the details.
It's not the point.
So we can get through the presentation first and then follow up on this afterwards.
Yes, that's okay. This is a really interesting conversation, and I'll just say one more thing before I move on. When we simulate the flux, there are too many parameters to tweak, and so we randomly sample all of the parameters at once. And in a single universe, you're going to get a random distribution of all the knob turns on all the parameters at once, and that's a single universe. So there's many different ways you can implement this, and the system may be probably is able to handle both. But let's compare notes about what CMS does in the discussion. So the many universe method, as we call it, is able to propagate many complicated effects by like letting the simulation do the work. Again, to get the lingo down, we call a lateral universe something that can, a source of uncertainty that can shift events between kinematic bins. So this is maybe a change in a calibration constant, which changes the reconstructed momentum or angle, for example, and that'll shift something between angle bins or momentum bins. This is contrasted with a vertical universe, which affects the weight that you fill your histograms with. So yeah, I think we're sort of on the same page there. That's just to get the lingo straight. So MINERVA's flagship product, which is something that we really haven't seen in the community, in my limited experience as a sort of a new postdoc anyway, is a histogram object that can help us out. So we call it the MINVHND, the N standing for many universes, or sorry, not universes, sorry, many dimensions. And this is a histogram container, which is built on root THNDs. And the basic idea is that it holds systematic universe histograms and groups them into error bands. So looking at this diagram here, this is our MINVHND object, which will fill with say, parallel momentum. And it has this TH1D object which contains the nominal simulation. So CV stands for central value, and this is our best guess universe. And then we group different universes into bands, and then each band has many different TH1Ds that correspond to the universes. So if you tweak a parameter in this universe, you're going to get this TH1D. If you tweak a different parameter, you'll get this TH1D, and so on. We use one dimension here, but it's also in 2 dimensions. So the critical thing here is that it propagates universes through histogram manipulations, for example, cross-section calculations. So the interface of the MINVHND is implemented by broadcasting the THND interface from root to each systematic universe. So each systematic universe, for example, will have an add. When you call add on the MINErva object, under the hood, each individual TH1 will be added together. And it's not just add, of course, any other root histogram function you can use to manipulate histograms and to do your cross-section calculation, so that at the end of the day, the final MINErva object will have the systematic, or the underlying universes propagated accordingly. Right away, then, we talk about extracting error bands from the MINErva. After you've done your whole cross-section calculation, you can extract then an error summary, which has the total uncertainty in black, and then the breakdown of all the different error bands in these dotted lines. There's a covariance matrix that can be extracted for each error band from the MINErva, where the elements are the averages of the values from each universe. And then the total covariance matrix is the sum of the individuals. So the variance is across the diagonal for the entire distribution. And right, so this is a correlation or between bins here. And this is how we extract the errors. So moving on from the MINErva object, each universe histogram will map to an instance of a basic class. So another way of putting it is, each source of systematic uncertainty, for each source of systematic uncertainty, you'll write a basic class. The CV universe is a base class, and then the systematic universe will inherit from the CV universe. And this uses C++ class templates quite heavily. So the CV universe will be the thing that interfaces with the event record and contains all the methods to calculate any kinematics that you might need to calculate your cross-section or whatever analysis you're doing. And then the systematic universe will selectively override behavior in the CV universe. Putting this into practice, this is what it looks like more realistically. In the MAT or experiment namespace, you'll have a base universe, which contains experiment management and optimization tools. If you want to define standard functions, you can do all of that in the base universe, so that the user really only needs to implement their kinematic calculations specific to them, and they can do so in their namespace, and they'll inherit from the base universe. And then down here with the systematic universes, there can be experiment-wide systematics that are living in the experiment or the MAT namespace. And then if there's a systematic that corresponds, that's specific to a group or a user, they can write their own, and they'll all inherit using class templates from the user CV universe. So in this way, the experiment can establish event-wide systematics right away. Or sorry, experiment-wide systematics, and making it very easy for a user to jump in. They'll just get the experiment standard systematics. As a very short example of what one of these classes looks like, you'll have, for example, calibration constant of the lepton energy, for example, that'll inherit from the CV universe, which is a template here. This is how we write it, though, to make it in public code so that every user can inherit from it. There will be some constructors, and then the most important thing is that the overriding the get lepton energy function will show how this systematic affects this variable. So for example, you did some study and you learned that the calibration affects the lepton energy by adding 50 MeV to it. And maybe you'll do a plus or minus here, or maybe you'll do some Gaussian throw. They're all options. right? So the user CV universe will define a nominal central value, get lepton energy, and then among other getters, and then the systematic universe will just override the single function that's needed. So as an example of what an event loop can look like, if you go straight to line 7, we have a for loop over the event record and a for loop over a container of systematics here. So you'll fill this container of systematics with instances of systematic universe classes. And then as you go through the loop, whether an event passes a cut or not will depend, for example, on how that systematic's specific kinematic function. So in this case, if we cut on lepton energy, then events that are shifted by plus 50 MeV may or may not now pass the cuts, depending on their universe. So a CV universe, CV event might pass, whereas a systematically shifted event might not pass. So in this way, in lateral universes, events can move in and out of cuts. And then vertical universes will shift the event weight. And then here we fill the histogram according to the universe, and then the energy and the weight. And this will fill the underlying TH1D that I showed you the map of earlier. Okay, so we are, I bumped up into my 20-minute slot with a little bit of conversation. I can spend 5 more minutes, I guess, talking about this last topic, or else I can go straight to wrapping up.
Since it was my fault, please feel free to go through the last little bit of your talk, and
Sure.
I can try to do what I was planning to talk about more quickly.
Okay. All right, well, I'll go through this fast. This is sort of a bigger question, taking a step back about how experiments design their data and provide access to users. I'm on the mu2e experiment now, and we are sort of just getting our analysis infrastructure online. And this is a question that I'm asking on this experiment, and I'm hoping to have some sway. But here's the deal. So the questions are, what kind of data is released to analyzers? How much general reconstruction does the experiment provide? How much low level or high level objects are there? What information is in the event record to calculate systematics? And then how much control do analyzers have over the info contained inside of the event record? The way I want to approach this is by looking at the case study, which is us, MINERVA. I think it's illustrative to look at what we did. So MINERVA releases data to analyzers with very minimal reconstruction applied. And then there's quite a bit of, there's sort of a bunch of infrastructure then that will allow users to run their own reconstruction. And in this way, in very big scare quotes here, we have this open source reconstruction development across the experiment. So users can study systematic uncertainties, they pioneer reconstruction techniques, and then useful systematics and reconstruction will be shared and absorbed into the general RICO. And this was a really awesome system for us. We're a pretty small experiment, and this was a really powerful way to do things, I think. One of the big benefits was that we had maximum flexibility with the expression of systematic effects. So if there's something like if you know that a systematic has a straightforward impact on an observable, then you can make the correction at the universe level. This is sort of like the plus 50. If you just know that the lepton energy is shifted by some systematic by 50 MeV, that's easy. You can just do that at the universe level. But if you have a more complex impact, if a systematic has a more complex impact on the observable, then you can let the sim propagate the effect, and then you can add that effect into branches wherever needed, and then users can calculate systematics, or rather the universes will calculate the systematics for you. But this system was very well suited to Matt's systematic universe classes, naturally, given that we built it. And it's not always possible for different experiments to do this. It worked out for us because data size and storage limits were good for us, and the computing needs were right for us. But sometimes data files are too big, experiments are too big. You can't have every user rerunning tuples and filling up tons of space. But I think that's just something to think about, because these decisions have bearing on systematic methods, how you implement systematic calculations, and that wrong decisions can handcuff analyzers. For MINERVA's case, it was very important that we be able to develop systematics, because measuring cross-sections, this is not some search or not. What we're trying to do is be very precise about cross-section measurements in order to probe models deeply. Okay, last couple slides. Internally on MINERVA, the MAT is used across the experiment to perform all the new analyses. I don't think anything published from now on will be using anything but the latest MAT system. We are reaching out to different experiments. We're beta testing the short-line baseline of the SBN program analysis. We are exploring Dune integration, Proto-Dune and Dune. We've given talks to both of those groups. There's a Snowmass white paper about our data pres effort and its relation to the MAT. And then I'm giving an upcoming VCHEP talk in the plenary session on Wednesday, which will be a lot of what you've heard today, maybe slightly less technical and more of general interest. The public release of the GitHub repository is forthcoming. There's one or two more projects that we're sort of wrapping up before we release it to the group, but we are open to collaborating with experiments and sort of working the system in. So in summary, the MAT is an analysis toolkit that is filling an observed need in the neutrino community. There's not a great systematic solution that we've seen. If we've missed it, by all means, we'd love to hear about it. Other analysis systems, while they may have modular systematics, they don't necessarily have the MNVHND object, which makes propagation of systematics so easy. Right, there's an emphasis on systematics with standardized transparent treatment, propagate, calculate. There's a lot of plotting utilities that I didn't mention with the MNVHNDs. And then basic objects are intended to be combined into higher level interfaces. So far, this has been used to apply to neutrino cross-sections. And what's next? There are a lot of places that we're wondering about going next. There's absolutely no reason this couldn't be applied to neutrino oscillation measurements and fits. And any particle searches, there's no reason why it wouldn't work. One of the exciting things that we're considering is inter-experimental shared systematics. So any experiment on the NUMMI beamline can in principle share the flux systematics. And so this is something that would make comparison across experiments very, very interesting. Machine learning workflows are something that are sort of still a question for us. MINERVA's machine learning program really has just been about improving reconstruction techniques. And then on top, once the reconstruction techniques are developed, then the many universe system can be applied and the MAT system can be applied. But other workflows I'm really not as familiar with, and I sort of need to hear about more in order to see how the MAT would work with them. And then beyond, this is sort of a big question about, in principle, there's no reason why this wouldn't work for other fields of science or anyone doing a binned counting experiment if you can hammer down systematics into the many universe method. And here we are. Yeah, I'm Ben. I'm at the University of Minnesota, primarily working on the MUDE experiment and still working on a lot on MINERVA. And then Rob and Andrew are in the on the call right now. And Rob is a postdoc at Los Alamos, and Andrew is a mature graduate student at the University of Rochester, and here's us. So thank you again for having me. And yeah. Very interesting group you've got here. Would love to do more, have more conversations. Thanks.
Thanks a lot, Ben, for this very interesting talk. I'm sure there's questions. Please use the raise hand feature if you have any questions. let's take a few now and then go on with the second presentation and then have more discussion at the end. Matthew, yes, please go ahead.
Hi, thanks for the very nice talk. So on, I think 1 or 2 slides back where you're talking about the papers. Yeah, so this is super great to see that you'll be at VCHEP. So I'm looking forward to those presentations there. And then my guess is you can't say too much more for the timeline, but you noticed you mentioned that you're going to be releasing this on GitHub, which is fantastic. That's something that I think we're all very interested in seeing. But when you say forthcoming, do you expect that to be this year?
Yes.
Okay.
Yeah, definitely within the year.
Okay. So
if
the
it
next,
were, yeah, go ahead. Sorry. No, please.
Well, I was going to say, I think all of us on this call are interested in getting to interact with this more closely and actually getting to look at the code and seeing how we might be able to have some interactions or overlap with you. What is the best way for us to keep abreast of updates on this?
I don't know that I have a ready answer for you.
That's okay.
I don't know. Maybe I would plan, a few months from now, dropping in to this group, maybe to this group meeting, or yeah, I don't have a ready answer for you. Maybe Rob.
Can I offer a thought?
Go for it, Rob.
So we are hesitant at the moment to just take what we have and make it public to the world because we know that there are some issues with the MNVHND class that we would prefer to try to solve before we let things run too wild and risk people latching on and never coming back for updates. But I think we are absolutely open to working with early adopters or, I think the folks on this call understanding our caveat that we want to try to improve some of these base classes, I think we'd be happy to share code with you in principle now. And in particular, if you've had thoughts on how to improve the base classes and maybe the motivation to help us do that, then that would be a different conversation altogether in a good way.
We could maybe invite you to the Slack that we have for IRIS-HEP. There's channels there certainly where we could also continue this discussion. Maybe that's a good way to stay in contact with each other.
Yeah, I didn't mention the traditional channels of email and Slack, but we're open there and we can be responsive, definitely on Slack for sure.
Okay, great. We can follow up on this after the meeting. Nick, yes, please.
Sorry, I was muted. On the slide where you have the sort of sketch code, yeah, I was a little perplexed. How does this passes cuts know which event it's in? Because I mean, maybe you just omitted a line where systematics is somehow tied to the event record.
We just omitted a line. There's a line that will go right here in between 8 and 9 that says universe set event, basically. Okay, and so that's where you sort of tie the event to the. Yeah, that's a great observation. It's really a pair, a universe event pair that needs to be fed into the passes cuts function. So, but the universe holds on to which event it's looking at it, and it updates it on each event. That's right. Okay. And this systematics object, that is just it's a container of universe, as it says. And each of those is defined sort of upfront statically and by these templating. Are you talking about the universes themselves or filling their universes? Yeah. So the base class might look something like this, where you have some constructors and then several functions that interface with the the event record. And then I can provide the slides too after. Maybe I'll send them directly to Alex and he can add them to the
so this
page.
looks like it's like a harness around the event record object that extends it sort of to dynamically provide alternative scalar values depending on what universe you're in. Okay.
Exactly. Yeah. Yeah. Universe by itself, we're sort of, injecting that word with meaning. It knows it interfaces with the event record, and it knows the idea is that in this universe, the calibration constants are this, and the model parameters are that. And so it knows how to calculate an event weight for resonant pions, or it knows what the calibration constant is. And so it calculates the lepton energy accordingly.
Okay. And then for each type of shift, each type of, let's say, axis nuisance parameter you introduce, you write some, or you write some function in this universe class to provide all the relevant variables you might be interested, considering that systematics effect?
Yes. So if this calibration constant has an impact on more than one function, not just the lepton energy, then you can override as many of the functions as you want.
Okay. And I mean, then I would be concerned about like code duplication. Is there some mechanism where like a composite function that depends on some more primitive functions is sort of automatically provided by like inheritance?
That's exactly right. Yeah. So I think I understood your question, although I'm trying to figure out the right way to answer it. So you see, for example, I don't know if this is exactly going to answer your question, but if we have some get energy function, then it'll be the combination of these two where we will call in each universe, we will correctly call the systematically shifted version of this function.
Right. So if that's overridden in a child class, then you'll get the appropriate shift even on the derived,
Correct.
The higher level quantity. Yep, that makes sense.
Okay, thanks a lot for this discussion so far. I would propose we continue now with our second contribution for today, and then we have some more discussion at the end. The second contribution is by Lindsey Gray. Lindsey is a scientist at FNAL, and he's also a co-developer of the Coffee package, which is a framework for columnar analysis. And he's going to share some thoughts from his perspective on this topic next. Lindsey, please go ahead.
So I don't have slides today because this is going to be a mix of going through what's on a GitHub discussion in Coffee that started from talking with Alex about his cabinetry project and how to decompose the multiplexing of systematics into filling histograms, and how to do this in a way that doesn't essentially allows us to express opinions about how systematics should be done depending on who we talk to, based on multiple lines of decades of experience across systematics, and also what tools are available to you to estimate those systematics. After discussion, I've been able to come up with some very first sketches of what tool code looks like in the setting of a columnar analysis. And it actually, after this presentation from the MINERvA guys, it has a lot of similarities, or at least it's something that can also cover what you do if you if you kind of translate what you've built into what this thing is doing. So I don't think there's any limitations there, and I think it could actually cover this if you were to switch to a columnar data processing system. It's just going through this in a different way of thinking about it. So I'll cut the story short. by going to the question that has, I think, generated the most thinking on my side, which is always trying to think about what other users think of what you've written and the tool chain that you've tried to build that you think is general, which is usually not. So Alex asked the question, how do other users handle the logic for systematics? Object-based systematics that affect all samples in the same way seem pretty straightforward. I agree with that. But that turned into a long sentence, but there's some problems when you go over to 2-point modeling systematics and things like this. Yes, and thanks, Alex, for the link. So yeah, how do you do this, or how do you handle systematics when you possibly need to join or have systematics that aren't simply, varying up and down across two different estimates for some source of uncertainty in a jet energy scale jet energy scale variation. So going down to the answer to that, yeah, so Nick has done a lot of work in his analysis for boosted Higgs to PB in terms of how to bookkeep and explode the systematics over a wide range of inputs, and also how to file them into histograms in an efficient way using HIST or the boost histograms with HIST on top, or coffee histograms. And in talking to some folks who work on Higgs to gamma gamma and CMS, one thing that they wanted to do was understand how to take that kind of approach, where you have good bookkeeping, build it into the objects, and then also have like basically slick, nice semantics for applying a cut over many systematic variations at once, which you can then use to drive drive iterations over different event selections and things like that. And so, yeah, and then the other questions, my responses here are mostly some ruminations about how you make good designs that don't write you or your users into a corner. I think I'm going to try to stick mostly to just talking about, so I've tried to think about this when making it, and we'll see that in a second, but I just wanted to go through and show you kind of the core idea of the things that we want to use to put together a systematics framework that's fast and extensible, and pretty clear to the user what you're doing. So with awkward array, you can take an array of data and make systematic variations over it pretty quick with just a few lines of code, and it's all here. The main trick is that you can add additional outer axes to even the.
Could you zoom in a bit?
Oh yeah, totally. There you go.
Great, thanks.
That better? Yeah. So the main trick is that you can just use broadcasting semantics to take a system or a systematic variation or a column of systematic variations over like all muons in the event in this case, and just multiply it by muon PT in this case in a very clear way, in order to make a triplet of columns that have all the varied muon PTs, and then instead of having to have the for loop on the outside and say, okay, I've got the systematic variation, we're going to take it from my take that from the list of variations that I calculated, and then replace all the muon PTs and the muons with that and make a new cut. You can move the loop down to C++ and also exploit vectorization, because you've got everything in contiguous array and memory behind all of this, and get a fairly a fairly compute efficient implementation that also makes it very clear in one line what you're doing. So you're back when you're manipulating your event to asking for just muon PT greater than 6.5 GeV in this case, because that's what I had to work with. And you've also said in that line that you're making PT variants, so you know automatically that you're asking for the outcome of this cut overall PT variance at once, and you get this into a combined mask, which you can decompose as follows. And we all thought that being able to label centrals ups and downs by 1, 0, or 0, 1, and -1 respectively was kind of cute, but that's kind of beside the point. But what we've got here is a pretty nice, concise way of taking a systematic and processing all of its outcomes in a compute efficient way that's also highly expressive. And that's like 10 lines of code to come up with an example of it. So it seems like the core of something that you can take and turn into a well-rounded idea. The next piece again came from some talking with Higgs to gamma gamma guys, and they were asking about how do you add the systematics together in a memory efficient way. So in this case, I did the easiest way out. And there's probably some code golf to make this look nicer, but generally adding systematics means that you have to come up with a rule for how you vary over all events for each of the systematics, and then additionally another rule for how two different sets of systematics add together with each other or with the rest of the systematics, because usually you have this compounding space of variations that you need to make as you add more and more systematics. And usually it's just kind of like this Swiss cross rule where you take variations along individual systematics at once, but sometimes for some systematics, you also take the full outer product space with all the other systematics to see what you get. It happens sometimes. But yeah, so this is just a very toy example of looping through each of the jet variations, each of the muon variations, and for the central value of the muon variations, taking the range of jet variations, and ditto for jets and muons. So you end up with a cross through the matrix of systematic variations that comes out of this instead of the full outer product. And yeah, again, very short. Seems like it's something that could be turned into a set of extensible rules. And then there's some talk about performance and maybe what we want for a minimum viable product. I don't know if that's actually something we want to discuss here because we're running out of time. And then some further discussion with people from Higgs to gamma gamma about applying functions and making things nice, stuff like that. So please read through that at your leisure if you're interested in the thoughts behind all of this and what's guiding our thinking. But now I'm going to switch over to trying to implement this. All right, let me zoom in. Is that big enough or is that good enough for everyone? Can you read that?
Yeah, I think that's good.
All right. Okay, so I just started with muons again, but tried to think a little bit more generally. And tried to exploit more of awkward arrays features. And right now the code's a little bit ugly, but I ran into an issue with awkward and I'm trying to understand what's going on, and maybe Nick or Jim has the answer for it. So yeah, I open our little test nano AOD root file that we have in Coffee. I get the muons out and then I implement this class. So there's some basic guards for ensuring that we have a list of systematics that we may decorate into the awkward array that describes muons and nano events, which is a package for lazily accessing data out of nano AOD files or other columnar schemas. And right. And just to make sure that the format's kind of common and always ensured. And I've also made it so that this class is something that we can mix on top of any awkward array, basically. So we have an additional representation that we can layer onto our awkward arrays that says this thing behaves as though it has systematics So this record will be annotated in interesting ways. Of course, you want to get a list of your systematics, so we just do that. We want our users to be able to define how they build variations through a fairly straightforward interface. This is probably really important. So you need a function that defines how you manipulate the output of another function that you pass in that tells you how to take whatever you're varying and apply the systematic variation to it. So you say what the systematic variation is, you say what it's varying, you also say how to vary it. And then if the varying function needs any metadata, you can pass that in afterwards. So it's up to the users to define this.
When you say what's varying, you mean like, for example, like the muon is being varied, or do you mean like the muon energy scale is being varied?
The specific thing in the muon, so the energy scale on the PT, for instance, because already you know that it's applying to muons, since you have to make a muon array that has systematic variations in order to have these functions anyway. Okay. We'll see it in the code in a second. Yeah, and then the part where you'll get into arguments at conferences is this one. So this I haven't even started to implement because I've been running into problems with the lower level functionality first. So the next thing, of course, that we need to define is how this specific systematic variation alters how you explode that systematic variation onto all the other systematic variations that you have on a specific object or in an event. Or anything else that has this systematic in its list of base classes. So this tells you how you keep making this Swiss cross or full outer product with all of the other systematics, and maybe it's even some other crazier variation on top, or way to sum over the variations on top of that. Right now, we don't do it.
Another clarifying question. So your point here is not about like the interaction between like jet energy scale and muon energy scale. It's more about how in this like nuisance parameter space you're going to probe off diagonal terms and stuff like that.
Precisely, exactly.
Yeah, I definitely, we did some design work on something like that at one point about, different options and ways of thinking about it and how it ties into downstream statistical tools. So at some point it'd be good to loop that discussion into this, what you're thinking here.
Yeah, absolutely. And yeah, I've just left it as abstract as possible. It's up to the user. And if someone comes up with a better way, you can change how your specific software stack works, or we can keep adding in base classes that make certain assumptions. Or if you don't like subclassing, we can figure out something else. All right, now into the meat of it. So how do we add systematics to an object? So this is what takes the name of the systematic, what that particular systematic is varying in that given object. And if I can find my mouse. Ugh, sorry, there's something, yeah, it's a screen in the backlight for me that makes me lose the cursor when it goes into Jupyter Notebooks. Anyway, yeah, what is varying and how to vary it. So we get all the fields. Or first we need to prepare the template object for what we're going to vary, because then we're going to loop after that after we build the variations. So then we get all of the variations from the user supplied function that's coming from the inherited class. I can probably skip making this template, but whatever. And then finally, we fill the systematics, we fill a new systematic variation with the name of that systematic variation, and then a new list of all the variants over that particular quantity of the object that we're varying. And then we decorate it with all sorts of types. So you can see here, there's this double awkward.zip that we're doing to turn it into a nested array beneath the the jagged list of muons that you have, in order to have another jagged list of muons within it that points back to the top of the list, except with a single thing removed right now. And this, I think, can be changed to removed and replaced with a systematic variation. And this can be replaced and changed, but I'm just trying to get to a proof of concept here. So what we've got is you'll be able to say muon.systematics.systematic_name.up, and as we'll see in a second, and you'll get the muon with the PT varied up. So implementing a standard systematic in this case, and now you get to see where I'm running into trouble. So here I've just implemented a standard up and down systematic for muons. I say I expect in this case that the way that I build variations on it is by doing all of this on an awkward array that has the two systematic variations for up and down defined, and they can be shifts or whatever. You get to define how the function works, and then it just immediately stores that and or stores that as a thing to be evaluated later, and then we'll call into it from a different function when we actually want to know the value. So we've taken the user function, wrapped the holy hell out of it, and saved it for later. And then if we want to get each variant, we do the same thing and say that at some point in the future, we're either going to get the 0th index, which is the upward variation, or the downward the first index, which is the second index, which is downward variation. And then we return what type we want this thing to be. And right now this is a bit clunky. We can do this cleaner. And then we say what's up and down. And then up in the base class, we know that all it returns is variations. And we loop over those variations. So if you wanted to, for instance, have something that has a much richer set of variations that you want to that you want to make for your event or your particular object, you can do this and it's going to automatically expand to that. So that's one thing I tried to keep first and foremost, is that it's not, this system is not particularly dependent on any certain format of applying systematics. And then finally, just some decorative things to make it look nice. So now in the current way it's set up, we take muons, wrap it in muon up down systematic, and we get muons with systematics. What systematic do we want to apply? So here I've made it into a shift systematic. So I've got plus and minus 5% on top of 1, perhaps as the scale factor or something like that. And then I know I'm applying it to a singly jagged array. So I add two outer indices and multiply it by the jagged array of PTs that's coming in from the awkward array itself. And here's where I'm doing some testing to make sure everything works right. But you can see here, now we have PT scale, PT, and then you just pass in the function that does the shifting, and it takes care of the rest. And now we have some looping over and diagnostic printouts and stuff like that. But down here, and you can see the problem here too, but down here you get something that's nice and expressive, which is that now you have objects that are representative of your systematic shifts that are in fact the full muon objects. So you could pass this to another function and run that function as though it's essentially in one variation of the mini universes or formulation that we were talking about earlier, or whatever name for it there is in CMS and Atlas. And so that's as far as I've gotten. And you can kind of see the problem that I'm having right now, which is that I'm getting an extra set of indices on the jagged array that I'm trying to put into the event that contains the systematic variations, and this is causing me all sorts of problems. And it seems to be coming from exactly these lines here. So I'll be on the horn with Jim about that, and we're already out of time. I'm sorry that was, I'm sorry I spent so much time going over the code, but I thought it was good to walk through it. I'll stop it there and ask you guys what you think.
Thanks a lot, Lindsay. I think it would be quite interesting also to put this notebook somewhere, so either we can attach it to the agenda or share it in some other way, attach it to the GitHub discussion or so.
Yeah, I sort of want it to work first, but okay. But I think it has some good ideas and some ideas worth discussing. So I'll do that.
Okay, thanks. Nick?
Yeah, so I'm trying to compare this to the previous talk. And one thing that strikes me immediately is the similarity in that both are trying to, or they're engineering themselves as harnesses around the input data so that when you go to query the input data for some value, you get some sort of transparently altered value.
Yeah, I think this is a good pattern to work around for analysis because it means you repeat the least amount of code or make the least intrusive edits to your code in order to get a huge table of systematics.
Right, and so on a user interface point of view, right, it's going to be critical that it's very easy for a user to come in and put a harness around their object in a lightweight manner without having to work too hard. And so, you saw with the templated, virtual method overrides of the universe class, and here you're seeing, I guess, sort of this.
Yeah, it's the columnar equivalent of that.
Columnar, yeah. It looks a little bit less user-friendly on the face of it, I guess. But that probably means
I wrote this yesterday, so fine.
Sure. That's one thing, though, that is different here is you still explicitly address systematic shifted variables instead of being inside a systematic shifted context. Whereas, in the earlier one, we saw that you're entirely in a systematic shifted context when you're doing whatever your subsequent analysis.
Yeah, I'm chewing on that one now that I've seen what these guys are doing. And my first reaction is that these two things, there may not be a difference between these two things if you code it right.
Well, I mean, it's a user interface kind of thing, right?
Yeah, it's really a UX thing, like it's more reflective of how you think about it.
I mean, I would say that's the most important, assuming you can get the underneath working the same.
Mm-hmm.
I mean, Lindsay, Nick, just as a one pithy line is, it would be great if, from the user point of view, once you had the code to calculate the cross section, it didn't really need to know about the systematics as much as you could have an external driver, which then accumulated.
That's what I'm trying to go for here, Gordon. By having the users say how you do everything. But yeah, I think it's worth thinking about how that intersects with what the MINERvA guys have done too, because I think it leads you in the same direction. These are two different ways of solving the same problem, and I think there's a better answer in thinking about both.
Thanks. Kyle had his hand raised. Let's take Kyle.
Yeah, no, I think, so I missed the first couple minutes of what you're saying. And I think if I understand the way you're using this term universe correctly, I mean, we did have this one, analysis framework and Atlas at the very beginning that basically got tossed, unfortunately, but called Event View, which also had this kind of paradigm of you look at each event, and when you're looking at it, you're kind of in the systematic context, so to speak. So one thing that I just flag, and I'm sure you've already started to think of it, is just how it propagates from kind of at the event level, what the systematic context is, to at the object level, what the systematic context is, especially when not all of those kind of variations apply to all the objects, right? So I think that's one thing that'll be interesting to think about. The other part is, I think building the systematics variations versus how it gets used as an object later could maybe look a little bit different on the user interface side as well, right? So you might imagine once you've calculated these variations, you might want to say I'm in this context, So now just tell me what the muons PT is, versus when you're building it, maybe it's there may be a different trade-off. Like maybe it's not necessarily like I'm in this context, but you're like, this is how you do this variation.
Yeah.
Yeah.
Yeah, I see that. So I think another way to think about this in the context, or given that maybe this context stuff is a bit more interesting for managing the events, or like doing the user code part of the systematics and trying to reduce code trash in your code and improve cleanliness and clarity of thought. So with respect to that, yeah. So what I'm seeing here is that in what I've cooked up recently here, based on discussions in that thread, is that we've got very fine-grained user-based definitions of how we make the systematic variations. But what I'm binding it up into is actually kind of similar to the context-based treatment that that we were talking about previously in the MINERvA talk, because you ask for a particular, essentially here you go into the universe of systematics, you ask for a particular universe by saying what systematic and which variation, and then you ask for quantities in that universe, or unless I've horrifically misunderstood something. So it's kind of a weird two minds approach to treating the systematics.
Yeah, so can I ask a related question here, which is kind of a separate point that I was going to say, is that, if you're in a situation where you're the systematic variation involves changing, the PT scale of muons up and the jet energy scale down, by whatever, and the, what unclustered energy by another thing or something, then the way that, it's not necessarily like systematic dot, this thing up, right? It's like, it's basically just like indexing into a bunch of different possible systematic variations, right?
Universes.
So that was one of the things I was going to say, is I'm not 100% sure if this class should be responsible for the thing that you're calling exploding. When we were thinking about how to, not filling the histograms, but how to build the statistical models that are going to then like interpolate between all these variational histograms. Like right now, his factory does the kind of axis, the cross like thing that you're talking about.
Yeah.
And so, so then we thought about, okay, well, we could support different types of interpolation algorithms that work if you do like the full Cartesian product. But then we said, well, we'd like to be able to have one that allows you to just kind of have an arbitrary mesh, right? So like you have a nuisance parameter space, you have an arbitrary mesh, and you want to just interpolate based on that. And that's like the most generic thing. But if you're doing something like that, that's not, it's sort of like some other tool's responsibility to decide where in nuisance parameter space you should go evaluate things. And then the kind of tool, it seems like this tool that's basically filling the variations would, in my mind, what would be clean potentially is to, outsource the way that the kind of generalized exploding is where you basically say like, here is a little mini database of all the systematic variations I want you to consider. And that gets passed in to this tool, and this tool then loops through that set of systematic variations and then does what it needs to do, as opposed to being responsible for the actual exploding aspect.
Yeah, I can see that the way you want to treat the rules is possibly not something that is really local to an object or even the event, and you might want to have some external driver that can have whatever information it likes. Though go ahead, Alex, or Lucas, sorry.
Yeah, so maybe one comment from the Atlas side. So the way that it currently kind of is an Atlas is maybe kind of like a third way that like the points that you can't even loop over, they're somewhat defined by the tools themselves that implement them. So it's not like, we can do like an external configuration that, like we run over these points in parameter space, but then the tools themselves, they kind of advertise like a suggested set of systematics you're supposed to be looping over. And so maybe that's...
Yeah, I mean, this is sort of covered by what I do in the subclassing, where you have, a particular kind of systematic that advertises certain kinds of variations within the list of variations that you return.
Yeah, I also had one comment on this context or universe idea. I think kind of it's attractive from a user experience perspective, and then the crucial aspect is probably how costly is it to switch to a new universe. And so if you imagine that you only have a weight systematic, you're basically just exchanging a single column, and so that should be as basically no op as possible, and so that there's not a lot of overhead of looping through like hundreds of contexts. And so I guess that's what like an event view would be, that you have like a set of semantic columns that you want to have in an event, and then like each systematic assigns one actual physical column to let's say UMP2.
If I can just interject quick, yeah, that is something that we do. So if it's a vertical shift, then we don't waste any time recalculating quantities or weights or anything like that. And we're looking for more ways to speed things up in more than just that as well, but in the same theme. Yeah.
So going back to Kyle's comment here, I think that with a little bit of thinking about being clever as to how you can index this systematics object that's inside of an object or an event, you can probably do the universe's interpretation with some reasonable organization of the underlying columns. It's really just careful thinking about the metadata and the way you store it. So I don't think any of these things are really destructive to what's being built up here. I need to think about it more and squint at it.
Ben, you had some reply to this?
I have sort of a separate point if someone else wants to go otherwise.
Oh, Nick, you also raised your hand at the same time. Was it related?
No, it's not related.
Okay. We are past our 1 hour, and I will have to leave fairly soon. I would propose to carry on this conversation on Slack. I will send you invitations to Slack if you're interested in continuing there. We can also make use of this GitHub discussion, but I think we see that there's a lot of similarities here and some differences, and I think there might be some more things to learn from each other here. So I think it would be great to keep the discussion going. And to see how much our efforts can be joined here and how much we can benefit from work that has already been done in the sort of respective groups. Any last urgent questions for this meeting today? And then otherwise we can continue the discussion offline, because I'm sure there's more things to talk about. Okay, if there's nothing else, then thanks a lot. Thanks a lot, Ben, for the presentation. Thanks, Lindsey, for showing us through this example as well. I think this was a very interesting meeting, and we'll continue the discussion offline. Have a good day, everyone. Bye-bye.
Thanks, everyone.
Bye-bye.
Bye.